So, it's a great pleasure to introduce Steve Balbus. Steve was born in Philadelphia and shortly thereafter studied maths and physics at MIT, whence he graduated in 1975 and went on to PhD in theoretical astrophysics at Berkeley in 1981. He then worked as a researcher at MIT and at Princeton before becoming professor at the University of Virginia in 1985. It was at the University of Virginia in 1991, working with John Hawley, that he made his signature discovery, the realization that accretion disks around black holes, if they're magnetized, would host a distinctive instability driven by the shear flow associated with Keplerian rotation, and that it was that instability, called the MRI, magnetorotational instability, that could be blamed, or if you like, credited, for triggering turbulence in accretion disks, enabling them to transport angular momentum, and thus to exist as accretion disks. So this was a paper that launched 1,000 papers, in fact many thousands. I looked it up today. It has over 3,000 citations today. Truly, with it, Steve has started a whole subfield of astrophysics, and arguably and importantly for people like myself, legitimized magnetohydrodynamics as a key modeling tool in astrophysics. In fact, he had worked before MRI and has worked since MRI on many other interesting topics. Inter alia, he discovered new gravitational and thermal instabilities of the interstellar and intergalactic media. So Steve is a man of many instabilities. Even after becoming arguably the Pope of accretion disks, he stayed intellectually restless, as popes sometimes do, jumping into new fields, including plasma physics, where he found another instability called magnetoviscous instability, solar physics, where he came up with a new theoretical model for the internal rotation of the sun, and most recently, general relativity, in which his interest was spurred when he had to step in to teach the subject when no one else was available, to Part B undergraduates. And this happened at a monumentally propitious moment just before the discovery of gravitational waves. So he has a good sense of timing, as you will discover shortly. A distinctive feature of his intellectual style has been to look at the kind of potpourri of much diverse physics that is present in any astrophysical object, to identify some very fundamental and previously overlooked physical process. In retrospect, it's usually obvious. A lot of good things in physics are obvious in retrospect. We all look back and say, why didn't I think of this? So then to analyze this process with great mathematical elegance, argue how it would make a key observable difference in an astronomical context. That's the program. It requires only three things to be accomplished: erudition, education, and taste. So it's easy. Invariably, after you do that, after he did that, a large hungry pack of numerical modelers and observers would jump in and turn it into a thriving industry. And so Steve has greatly helped to keep our field intellectually alive and more, or as importantly, its practitioners safe from unemployment. As you will discover today, he has been ranging ever more widely indeed in recent years, and has made this truly interdisciplinary leap from astrophysics to evolutionary theory, a kind of Renaissance move that no one ever makes anymore, but which probably would not have surprised his early predecessors in the Savilian chair, such as let's say, Christopher Wren, perhaps. Anyway, so in 2004, being a Renaissance man, he left the United States in search of civilization, and became professeur des universités at École Normale Supérieure in Paris. In 2012, he was elected the Savilian Professor of Astronomy at Oxford, a chair which incidentally was founded by none other than our very own Henry Saville, famous Warden of Merton. A year later, in 2013, for his work with John Hawley on MRI, he received the Shaw Prize in Astrophysics, which is one of the greatest honors in our field. Also financially, incidentally. It's worth $1 million. Which in Oxford meant that he could afford to put a deposit in a small suburban house. In 2015, he was elected to the United States National Academy of Sciences, and in 2016, he became Fellow of the Royal Society. So this collection of the highest honors in the academe has remained woefully incomplete until tonight, when he rises to the pinnacle of all achievement to which any physicist can aspire, and becomes the 30th Ockham lecturer. So, ladies and gents, here's Steve Balbus.
Talk about a tough act to follow. Thank you, Alex, for that generous and singular introduction. I only wish my mother were here in the audience, and at least somebody would have taken you seriously. Let me begin by explaining why I like to do astronomy, or what attracted to me to astronomy many years ago now in the first place. And that is that it's one of those subjects where you can get to profound truths with seemingly innocent observations or insights. So one of my favorites is, you may have noticed, it gets dark at night. Why it should get dark at night turns out to be not so obvious, because the universe is full of stuff. And if you set about trying to calculate in a naive way what a universe sort of full of stars, homogeneously distributed, would be, the answer turns out to be infinite. And the resolution of that problem is very far-reaching. It turns out that the universe must be finite in space and time. So I'd like to begin this lecture with another innocent observation, if you will, and that is that, I guess if it gets dark at night, is probably the oldest astronomical observation I can think of. The second oldest, probably that the sun and the moon look like they're the same size. And viewed from the Earth, it's about 30 minutes of arc, half a degree. This is generally written off, if you look in textbooks, as just a coincidence. What else can it be? It just depends on where we are and where the moon and the sun happen to be, that their sizes were such that it just so happens that they look almost exactly the same. And it just so happens to be on a planet that's full of life, and just so happens to be on a planet that has all kinds of things. It's another one of those coincidences that you simply have to tag on. Now, of course, the fact that the sun and moon exist, that they're the same size, does something besides make nice eclipses. And one of the things, and perhaps something very important, is that the gravitational fields that are exerted by the sun and the moon, in particular their tidal forces, are also very nearly equal in size. So let's remember what a tidal force is. So on the diagram there, so at the point P on the surface of the Earth, where you may have an ocean, the balance of forces, which is exactly met right at the center of the Earth, where the gravitational force and the centrifugal force are balancing precisely. If I go a little bit to the Earth's surface, onto the Earth's surface, that's not quite the case. Here's the moon, and on the surface of the Earth, I'm a little bit closer to the moon, at least on the near side, than I would be at the center. And the radius of curvature, or the radial distance from the moon is a little bit smaller, so the forces don't quite balance anymore. They nearly balance, but there's a tiny little residual. And I've set up certain coordinates here, U, V, W. W is along the centers of mass of the systems, and U and V are coordinates which are perpendicular to that. And in those U, V, W coordinates, I've written down the mathematical expression for what the excess tidal force would be. There is an amplitude, G m over r cubed. So that's Newton's G times the mass of the moon divided by the cube of the distance between the centers of mass. And then those linear coordinates, minus U, minus V, 2W. So you'll notice that the amplitude in front is proportional to 1 over r cubed. In a technical sense, what we're doing is expanding a Taylor series. And if the Newtonian force is 1 over r squared, the next term in the Taylor series is of order 1 over r cubed. And that's very interesting. You notice that the sense of the tidal force is to squeeze inward, that's what the minus sign does, along U and V, and to extend outward along the W direction, which is the line of the centers of mass. And so here's the sense of what it would do to an ocean. Now the Earth, of course, responds to the tides, but the ocean responds more to the tides. So the oceans tend to get, at least in the configuration there, somewhat bigger or higher near the equator, and that water comes at the expense of the oceans near the poles. You notice that there's two sides to a tide. It's not just pulling more strongly on the near side, it's also being flung out centrifugally a little bit more strong on the far side. And approximately, sort of leading order, this is a symmetric problem. You have two bulges, you have on the pole side, the way I've drawn it here, you have a little contraction, and that's the way the tides work. 2 high tides a day. Now here's another coincidence. Even though the masses of the sun and the moon differ by orders of magnitude, the sun is 10 million times more massive than the moon, and their distances are vastly different. The sun is 1,000 times farther away. Somehow, those tens of millions and thousands all disappear. And at the end of the day, relative tidal strengths are within a factor of 2 of one another. Another fantastic coincidence. How long are we going to put up with this? So let's get a few basic facts straight. The matching size of the tides and the matching angular size, that is to say the matching angular sizes of the tides and subtended angle, that's not 2 coincidences, that's 1. Because even a rough agreement in tidal strength turns out to mean that the angular size that you perceive must be very close. That sounds strange. Let me walk you through the mathematics of that. So there on the top left, I've written down an expression which says that let's start out with equating or roughly equating the amplitude. So if I want the 2 tidal forces to be about the same, I set m moon over r cubed moon equal to some fudge factor, f. That's going to be a number of order unity times the mass of the sun divided by the cube of the distance to the sun. But if I write the mass as something proportional to an average density times the diameter cubed, do the same things on both sides of that equation, Well, you notice that everything depends only on the ratio d over r, which is the angular size that we perceive from the surface of the Earth. And so if I solve that equation for d over r and set that equal to theta m, then you see theta m, the angular size subtended by the moon as seen from the Earth, d over r, is in fact equal to theta s, the angular size of the sun, times a density ratio and that fudge factor to the 1/3 power. So it comes in very weakly. And the sun being a star, the moon being some kind of a solid, that's about a factor of 1/2, and F itself, if I'm on a planet where for some reason I want those two tidal forces to be the same, that's going to be a number which is not very far from 1, and when I take it to the 1/3 power, it's going to get even closer to 1. So if for some reason there's something about why we are here, remember it's conditions probably are not such that life appears spontaneously every time you have a habitable planet. But if there's something in addition, like the tides are involved, and I want those two to be comparable, then it follows that it's not such a coincidence that the angular sizes are the same. So the question to be asking is there some reason why we should be on a planet that has two sources of tides, and those two tides to be of approximately same amplitudes? So this is simply a graphical representation of what I just went through with the algebra. The conclusion is that the real importance of the angular size agreement is that it reminds us that the two tidal forces are comparable. This was actually known immediately to Newton once he had his theory of gravity, and used that argument of equal angular sizes to deduce that the density of the sun had to be less than the density of the moon by about a factor of 2 based on the relative height of the tides. He was a very clever guy. The nice thing is that if we're talking about tides, we're talking about forces, we're talking about dynamics. At least there's something to sink our teeth into here. There's something we can work with rather than perceived sides or sizes. So this has physical content. So the question is, does it have anthropic content? Is there some reason that having two tides was somehow important to our ultimately being here? So here is the setup. This is the celestial sphere. So the Earth is kind of at the center of this celestial sphere, and that sphere is the projection of the sky. And the red circle is the celestial equator. You take the equator of the Earth and sort of paint it onto a great big sphere at infinity. The north celestial pole goes through the Polaris, through the North Star. And then the ecliptic is the apparent path that the sun takes in the sky throughout the year. And the moon is not quite in the plane of the ecliptic. It's inclined by about 5 degrees. So from our point of view, we're kind of sitting in the center, and once every 365 days, the sun goes around on the ecliptic, and once every 27 point something days, the moon goes around on its orbital great circle. So in other words, we have two things with similar forcing tidal amplitudes. The moon orbits with a frequency of 2 pi radians divided by 27.3 days, and the sun with a frequency of 2 pi divided by 365 days, which at first sight looks very different, but of course, since the Earth is spinning around once a day, that's a big frequency. And so the effective forcing frequency is actually, for the moon, that's the omega m, 2 pi radians times 1 minus 1 over 27.3, and the effective frequency that we feel from the sun looks pretty much the same, except that it's 1 over 365.25. So those frequencies, the rate at which the tides are excited by the sun and the moon, are in fact very nearly, but not quite, equal. And this is saying the same things now, going from frequencies to periods. So, I'm addressing a physics audience. What happens when you have two periodic functions with nearly, but not quite the same frequency and comparable amplitudes? You get beats. So what happens is that the sun and the moon come into phase and then they go out of phase. And if their amplitudes are comparable, as long as one is not completely dominant, you will get an appreciable difference in the size of the tidal forcing. And that starts to have physical consequences, because the net tidal force, and therefore the resulting tidal displacement of the sea, will be strongly modified. I repose the question, is there something about that state of affairs that is somehow anthropic, somehow related to us being here? The point is, from one high tide to the next, the sea level will not be the same. You need this state of affairs to have something like an intertidal zone, something that has been incorporated into the life cycles of countless marine species. But intertidal zones don't just happen. They require, as we've seen, just incredible astronomical fine-tuning. Now, the thing about these intertidal zones is that they have significant consequences. Perhaps tidal dynamics might have been at the heart of some kind of a unique evolutionary event, an event essential to the evolution of a contemplative species. Well, perhaps the most important evolution, one of the most, I don't want to be, that's a competitive statement. What was the most important evolutionary event to occur? Certainly a contender was the fact that aquatic vertebrates left descendants who were able to adapt to the land upon leaving the sea. That has happened only once in the history of life. The other way around happens all the time. You can't keep creatures out of the water. They evolve out, they go back in. Reptiles become ichthyosaurs. Foxes become dolphins. Dogs become seals. They can't get enough of it, even though it's pretty dangerous in there. Only once did it go the other way. And that occurred in the Devonian period. It's about 400 million years ago. The sort of Cambrian explosion, where multicellular organisms appear in the fossil record, is 550 million years ago. The question is, should we have expected this just to have happened eventually, that the vertebrates would come out of the sea, or did something precipitate this? Well, let's go back and look at the tidal question. Inland tidal pools, what people who do this subject seriously call upper intertidal zones, that are formed at one high tide, if it happens to be a high tide at the top of the beat, that may not be replenished from one day to the next. The waters come in, they go out. You may not see water coming in that far again for a period of, depending upon exactly where you are, up to months. And over the course of time, there will be environments where you get a whole network of isolated intertidal pools. Here's a cartoon picture. Here's a high tide. There's a school of, I don't know whether lobe-finned fishes form schools, but let's assume it does for the sake of my talk. There's a high tide and kind of a bumpy bottom. The next high tide that comes in, well, you can see the problem. The isolated tidal pool is going to be in difficulty, and unless that creature learns some land navigational skills, there are all kinds of dangers that it faces. Just to look at this quantitatively, here's an actual calculation of what's called the equilibrium tidal forcing, kind of that function which I showed to you earlier in the talk, where I put in models, or I put in numbers that are appropriate to the moon's orbit at the time of the Devonian. In this case, it's just for the sun. This is without the moon. So the sun by itself in the open sea would cause a shift in the height something under 20 centimeters. Now here's what the tidal forcing would look like with those same Devonian parameters, but if the moon had the same density and half the diameter of the sun, and here's what the actual tidal forcing of the moon together with the sun with Devonian parameters looks like. So it looks like there's kind of this funny stripe at the bottom. That's actually the fact that the tide occurs twice a day, but for the particular latitude I chose here, which I think was 45 degrees, it doesn't come up all the way to the top for the second tide, so it looks like it's shaded. But that's really just a continuous mathematical curve. And the point is, you can see how quickly the tide falls off from one day to the next. So there's the scale at the bottom, 21 days between the two markings there. What are the consequences of that kind of sculpted tidal pattern for the transitional tetrapods, as they're called, the first creatures that made the transition from sea to land and had their fins develop little digits that enabled some degree of land terrestrial navigation. Again, high tide, low tide, the next high tide, and then low tide, and there is an isolated tidal pool. So the question is, we're speculating, what were the tides actually like at the time of the Devonian? Well, that's an interesting question, because in the last several decades, the geophysicists have gone through a great deal of trouble trying to figure out what plate tectonics say about the distribution of the land masses throughout geological time, and in particular throughout biological time. So here's a fairly standard reconstruction of what the Earth looked like in a Mercator projection, sort of projected onto a cylinder, at the time of the Devonian. So this is in fact the late Devonian, 370 million years ago. One of the interesting features there, you'll notice, is that there is a very large wedge that's carved out on a planetary scale. Now, interestingly enough, on the current Earth, there is another configuration like that on a much smaller scale, the northwest portion of Australia, and the tidal ranges that are associated with Australia, tides on the northwest corner of Australia that are some of the highest in the world because the distortion is focused. It's excited at the western end, waves travel down the channel, and the tides become very high where they're constricted. We see similar high tides locally in the English Channel, in the Bristol Channel, and of course the highest tides in the world in the Bay of Fundy, which has helped, in addition to constricting the tidal waves, it also has a resonant condition such that the frequency of the driving and the natural sloshing frequency in the bay are close to one another, and that sort of configuration of two events causes the largest tides in the world. And there, for comparison, is the situation in the Devonian. In the late Devonian, the eastern regions of the upper continent, Laurasia, and the lower continent, Gondwana, contained an entire subcontinent-sized bay, narrowing down to just intercontinental shallow straits. So this is an interesting and very scaled-up version of what we see today, as we've seen in the Bay of Fundy, the Bristol Channel, and other locations that are famous for their tides. What was the Devonian period actually like? Well, the Devonian was a time of very heavy forests. The first trees also evolved at this period. Archaeopteris, not the bird Archaeopteryx, the tree Archaeopteris, grew to 30 meters in size. It loved wetlands. It was the time of the first deciduous leaves. Leaves had to be invented. Deciduous leaves means plants went through all the trouble to evolve leaves and then threw them away because they could grow them again. It was easy to grow leaves back then because there were no herbivores. Why bother carrying them around through the cold season when the sun may not have been as high? There is fossil evidence at the time of the late Devonian for black shales, which indicate some kind of a large inflow of organic material, and widespread anoxia. Something was taking all of this dirt. Dirt was invented in the Devonian. There was no dirt before the Devonian. It was clay, it was sand, it was gritty stuff, but to get real mud and dirt, that took organic material, and that didn't evolve until the Devonian. And at some point, all of that was washed into the seas, and it precipitated what appears to be one of the great mass extinctions of all time. So this is another feature which we'll talk about, because this also may well have been related to tidal dynamics. Let's talk about the paleogeographic context now. Here we are in the very earlier, very late Silurian period, 430 million years ago. You see there's more of a kind of a mid-ocean between the two supercontinents, Laurasia on the top, Gondwana in the south. The beginning of the Devonian, that turns into more funnel-shaped. In the late Devonian, you can see it becomes very broad and then very constricted. And I managed even to find something to show you what this looks like projected on a globe rather than a Mercator projection. And that gives you a bigger sense on what kind of a planetary scale that kind of opening looked like on the surface of the Earth. By the early Carboniferous, that's the period after the Devonian, that big channel is starting to fill in. The late Carboniferous, you can see the two continents starting to come together to form a supercontinent, and at the Permian, that becomes Pangaea. So that's the overview of where we are, and it was right, I shouldn't say, I mean, it was over a period of tens of millions of years, but it was at the Devonian period when the actual transition occurred and when the tidal dynamics might have been interesting. So, what do the simulations actually show? So here are some honest-to-goodness calculations, some hydrodynamical calculations that my colleagues at the University of Uppsala and the University of Bangor carried out using the reconstructions of the geophysicists to try to figure out what the tides may have looked like at the time of the Devonian. And we have a reconstruction of 400 million years ago and 370 million years ago. And where you see all that red, those are regions of particularly high tidal amplitudes. And this is an interesting game because you need to say something about continental shelves. You need to say something about the depths of what they call the abyssal plains, the deepest parts of the ocean, excluding things like trenches and ridges. So there's a lot of guesswork that goes into this, and What you want to be able to do is to do many, many, many of these runs, which we're in the process of doing right now, in order to get some kind of a feel for what the statistical distribution of the tidal patterns are, and whether there are features that you see in these calculations that are robust. So the hypothesis would be that where the tidal ranges were particularly large, those might be interesting areas to look for fossils. Or, if fossils have already been searched for, you ask the question, are regions where we see these big red spots associated with key transitional species? So there are the calculations, so bear in mind where the red spots are. And this is taken from a textbook from 2012. And the red spots on the southern coast of Laurasia, and then in the South China, what is now the South China portion of Gondwana land, there have been a number of key transitional species that have been identified. So there's the calculation from 370 and 400 million years ago. And this is the biology. Suggestive. Now, the idea that I've sort of put forth is actually one that dates from the 1930s. There was a great paleontologist, Alfred Romer, who argued that, using some jargon now, weight-bearing Scheridian limbs, those are fins that kind of developed finger-like appendages, were an adaptation by lobe-finned fish driven by the obvious selection pressure of being able to flail seaward to a deeper tidal pool, or a tidal pool which is replenished more often, when their own isolated tidal pool turned inhospitable. I couldn't resist. These are Romer's. Now, Romer's argument, in my view, fell out of favor a little prematurely. He argued that the red clay sediments, we're getting into a little bit of sedimentology here, in which the early tetrapod fossils were found, were typical of arid conditions. So the idea is that the pool's dry, stranded fish that can manage some degree of out-of-water navigation will have more baby fish. The problem was that subsequently it was understood that red clay sediments don't reflect arid conditions necessarily, and also that the sediments may not have been representative of where the tetrapods were originally laid down. So there followed incredible arguments and fruitless wrangling about the real reason why fish develop legs. I think we can all imagine that there are obvious advantages, if you're a fish, to having little paddles on your body. If you live in choky, swamped, intertidal wetlands with a vast network of available pools. There need not be any one particular reason to get from one pool to another, say, that was responsible for the development of this particular form of tetrapod morphology. There is a nice explanation, though, which is my personal favorite. I hope it turns out to be right. The French have weighed in, it was for better sex. I'll go with that one. Clearly, there are good reasons to try to leave a shallow, brackish puddle, even under non-arid conditions. And in fact, we see that today. We see things in Southeast Asia climbing perches. And the only time, it seems to me, that it would make sense to develop or to adaptations to get out of the puddle is, in fact, if you're going to be moving through conditions which are swampy and humid, not a desert. If I were a drill sergeant, I would tell the recruits, if you are in a puddle, you stay in that puddle. You do not leave that puddle. And you just hope, because if you walk in a desert, that's going to be the end. On the other hand, if conditions are humid, and that appears to be what the real Devonian was like, then there's an obvious selection to being able to move around. And there are many, actually, we see that in many species today. I list some of them on the slide here. To make matters more interesting, there were what are known as the Iphilian trackways. So the Iphilian is a particular sub-period within the Devonian, And what happened was in 2010, at a time when there should not have been any tetrapods, they found feet tracks. Not primitive feet, but real feet. 20 million years before they should have. These things were walking. That means the line must have branched several million years before them. So these are highly developed, specialized, five-fingered pentadactyl limbs. So obviously the tetrapods that developed later and the closely related actually these early tetrapods and their closely related lobed fin fishes coexisted extensively, rather like birds and dinosaurs. The birds came from dinosaurs, the dinosaurs remained, they coexisted over a long period of time. Something bad happened to the dinosaurs, the birds continued. A similar story seems to have been in store at the end of the Devonian. Where did they find these creatures? They found those creatures right along the southern shores of Laurasia, which is also an interesting region from a tidal point of view. So, what do the actual paleobiologists have to say about this? Well, probably the most eminent person in this field, Jennifer Clack, has written a fascinating textbook, Gaining Ground, it's called, great name, for the evolution of vertebrates at the time of the Devonian when they made the sea to land transition. So she says, you can read it, the discovery of the Aphelian trackways from Poland, it's in modern day Poland, in a shallow sea has prompted yet another scenario. I haven't coached her on this now. For why tetrapods might have left the water. The suggestion is that in the intertidal zone, her words, many fish may have been left stranded as the tide retreated. Tetrapods may have evolved to exploit this resource. So what she has in mind there is something more interesting. This is the creation of the smorgasbord. You have all these trapped fish, some of whom, well, many of which are not going to be particularly good at land navigating, whereas the ones that develop land navigational skills will go around and have a little of this, a little of that, and a little of this. So it's a nice way to feed. I like the idea of them figuring out how to get back to the sea rather than spending the time out of the land feeding, but obviously both could be going on. Let's learn a little bit more about the tetrapod habitats. For a while, the scenario was that tides were not important because tetrapods were associated with freshwater conditions, not marine conditions. Clack writes, the assumption of a freshwater origin for tetrapods has recently been strongly challenged. Among more recent finds of early tetrapods, there are many now known to come from tidal, marginal marine, or brackish water localities. And in fact, we now know one of the richest sources of tetrapod and tetrapodomorph. That's a fish which is very closely related, but not quite a tetrapod, but obviously in the process, kind of a missing link between a standard lobe-fin fish and a fish that has usable limbs. A tetrapodomorph fossils comes from a huge tidal delta in what is now been spread over Latvia, Lithuania, Russia, and Estonia, known as the Baltic Devonian Delta. This is a river delta in sort of estuarine conditions where you had substantial tides and mixing of both freshwater and marine conditions, and obviously it would be an environment where you would have a huge network of tidal pools and ample opportunities to go from one to the other. The tidal plain was graded, which means it was particularly, that is, it was on a slope. So it would be particularly sensitive to modulations in the tides. If you had a high tide, then it would go uphill quite a way, and then one which wasn't quite as powerful would lead you a long way from the stranding tidal pools far inland. And it's even possible to extract remarkably detailed about the tidal conditions from the sediments. It shows this particular Baltic Devonian delta shows direct fossil evidence for intermittency. The sedimentation in the upper plane was clearly sporadically interrupted by spring tides. So spring tides in this sense doesn't mean springs of water. Spring tides is the large high tides, spring tides and neap tides. To give you some idea of what it looks like, the authors have pointed out a modern day equivalent. So this is the Ockham River Delta in East Kalimantan, Indonesia. So there's a satellite photograph. So this is the analog of the Baltic River Delta that was so fruitful during the Devonian. So the modern day one has a span of 50 kilometers. Gives you some idea of the size that we're talking about. The Baltic Delta, you have to expand by a factor of 10 in each dimension. So this was a vast breeding ground for biological adaptations under conditions that were heavily influenced by the tides. And there's the current location. The tidal records from the mid to late Devonians are now complete, and the records show that from the earliest mid-Devonian sediments, where much of this was going on, there were 12 feet difference in the tides. All right, what else? Let me try to wrap up. There's recent evidence that tetrapods existed in what are known as Urahalline ecology. More jargon. That means mixed freshwater and salt water, and they get that from isotopic evidence from the fossils. Again, an indication that these evolved in tidal basins. What happened at the end of the late Devonian? So here are two paleobiologists writing in 2007. A combination of climatic, plate tectonic, magmatic, and still poorly understood paleoceanographic factors caused the recurrent sudden perturbation of stable ecological conditions by short-term global events of variable magnitude. I think what is inevitable here in this scenario is that as the continents are closing, you're passing through planetary-wide tidal resonances. And that has the effect of not only raising the sea level, but the more vigorous activity of the tides is well known, and we see it today, in terms of mixing of organic nutrients into the into the waters, which in fact seems to have occurred on a tremendous scale at the end of the Devonian. It's a little bit like dumping your lawn clippings into a stream. You're not supposed to do that because it decays, and the bacteria rob the waters of the oxygen, and that seems to have happened on a massive scale. Still not understood. A synthesis of a special Devonian. Let me put my cards on the table. There was a confluence of highly modulated tides and a receptive geography that led to a vast network of isolated pools and planetary scale swamps. Heavily forested, deciduous trees and dispersed seeds were widespread, and the accumulating plant debris in swamps, when combined with these unusual tidal conditions, resulted in a background of slowly decaying organic materials and anoxic waters. But a subclass of lobed fin fish evolved in this kind of environment with fingered digitized limbs as a navigational aids for both aquatic, probably, and semi-aquatic environment. These tetrapods apparently coexisted for 18 million years with their ancestral cousins without becoming the dominant line. We only have footprints. We have no body fossils, and it's a mystery. It's a mystery why that is the case. Whether it's biological or whether it's sedimentology is not clear at this point. And then at some point, the shallow water dwelling lobe-finned fish were decimated by the anoxia. Those fish which didn't become tetrapods were completely and totally wiped off the face of the earth. They were the dominant fish line. The fish that we know today, the ones we like to eat, those are the ray-finned fish. They were completely subdominant at the time. All of the lobe-finned fishes disappeared. Every single one, except lungfish, coelacanth. Coelacanth was discovered only in 1936 in the Indian Ocean. There aren't very many of them. So it was a huge event, and it was the tetrapods that survived, took over. And the ray-finned fish, the other kind of fish, who could fill the niche left by the lobe-finned fish. The offshoot tetrapod line had more options, more attainable niches. Roamers thrived. Closing perspective. The sun and the moon appear to be the same size in the sky. Remember, that's what we began with. For me, this is an astronomy fossil, and it suggests an important role for sizable, highly modulated tides in the history of life on Earth. I think this is supported by the biofossil record, and I think it's incredibly unsatisfying, indeed intellectually bankrupt, to write it off as a coincidence and move on. By contrast, its adoption organizes several strands of thought that have been shared by many for many decades, really since the work of Romer. It suggests a particularly fruitful direction of inquiry as well, which is now, can we develop a theory of paleotides, which would be independent of the question that I've raised today, something that would be of considerable interest for people who are interested in trying to understand astronomical events in terms of where the Earth, where the moon has been throughout geological time, because the moon is moving in response to tidal dissipation, and knowing how to calculate that in some way for a given configuration of continents is an interesting problem in its own right. And of course, ultimately, maybe it might just explain why we're here. I think that is a good note to end on. Thank you very much.
Thank you, Steve. This wasn't the only reason why we were here, because we were also here to ask questions. So call on the tetrapod in the audience to ask questions, please.
Thank you for a highly impressive lecture. So I have a couple of questions. The first is, it's my understanding that the moon had a much closer orbit to the Earth during the Devonian period, and since its formation of the moon, its orbit has decayed over time. So I was wondering if you've incorporated that into your calculations, because I'd imagine that means the tidal impact of the moon would be even greater during the Devonian period than it would be today. And my second point was, I'd be very interested to know what paleontologists think have found about the diet of these stem tetrapods. So if they can find stomach contents, for example, or the dentition, the teeth of the stem tetrapods, if they would indicate a diet which is rich in land-based plant material or land-based insects or arthropods, that would definitely support even more firmly your idea. So just two points.
Okay, so I'm much more comfortable with the first question than I am the second question, which gets me out of my comfort zone, but I'll try to come back and do what I can with that. In answer to your first question, yes, of course we took that into account because it's very important in trying to get the right. There's two things that happen. The moon is closer, not a huge amount. It's perhaps 5% closer, and that means 15% difference in the tidal patterns. It's 385,000 kilometers today. That's the semi-major axis. Probably at the time of the Devonian, it was 365,000 kilometers. I'll leave it to you to calculate as a homework problem what the length of the day was at the time of the Devonian, conserving your angular momentum. That's actually that's an interesting part of this whole game, to be able to calculate. That's a hard problem, actually. Not the one I just gave you, that's an easy problem. A hard problem is to figure out what the tidal dissipation history was. And because if the moon, right now it's moving out, it's not decaying, it's actually moving out at 3.8 centimeters per year. And if you follow that backwards, then the moon crashes in only 1.5 billion years ago into the Earth, instead of 4.5 billion years, which is what we believe would be the proper time. So we have a lot more tidal dissipation going on today than we would on average over the course of the Earth's history. And these kinds of calculations tend to verify that, because the Atlantic is in a near resident condition. And so the tidal response is bigger, and you have more dissipation than you think. In terms of what the fossils look like, there isn't a very complete fossil record from 400 million years ago. Generally, these creatures didn't, at least the particular, I guess the answer is there just aren't enough of these transitional species in good enough shape that we can do anything with them. To get a fossil where the soft organic material is preserved well enough that you can tell what they ate is pretty damn hard, and it's overemphasized a bit because when it happens, it is so spectacular that you get media coverage of something, you know, there's some Burgess shale in Canada or something or other in the Gobi Desert, it's always turning up. And so you think that's just the way normal fossil finds are. No, many of these species are identified by a jawbone, and that's it. So you don't have, I agree with you, and it's actually, you're thinking along productive lines, but at the moment there isn't very much that we can do sort of reconstructing what the diet would be. It'd be great if that comes to pass.
Thank you.
I was wondering how likely it is for the shape of a continent to have many places where water can actually get stuck after high tide. Given that, so if you look at the profile of, say, Europe, it doesn't have a lot of local minima, and the water seems to flow towards the sea in most cases.
Yeah, usually what you're talking about is something like a very, as I said, perhaps that's a good point to emphasize. What we're probably talking about is a very broad river delta. So the cartoon picture that I drew, as you say, that was just mostly to illustrate the point of principle. If I were to go back and draw it more realistically, it would look like a much more extended, very large tidal plain, where you have, rather than a nice isolated tidal pool, kind of a whole swamp of varying degrees of depths. But your point is well taken. It's probably not going to be quite so clean as I made it out in sort of the cartoon picture. In general, it's very hard even to a lot of these things, we wouldn't be able to reconstruct the Bay of Fundy either, because that's a very local condition. So one of the things that surprised me is I was skeptical at first with the calculations, but I had a student who did a master's project where they took the Devonian and turned it into a cartoon. That is to say, he had these polygon continents, and he just sort of moved them around. And the gross tidal pattern was actually rather robust. And with the reconstructions that we've drawn that shows lots of these very large tides in sort of the northeast corner of Gondwana land, that actually also seems to be insensitive to the details. So that's something we're trying to figure out, and at least it's encouraging that we're not completely wasting our time.
So what would happen with multiple moons or like binary stars?
Well, can I twist your question to my advantage?
Yeah.
What I would say is that if you're trying to look for interesting habitable planets, you should look for exomoons. I'm not sure whether that's essential for the origin of life, but I suspect that something like that, I think a life everywhere will naturally evolve in water. And then the hard part is to get something which has evolved under conditions where its entire locomotion system is based on hydrodynamics, and its entire respiratory system is based on gills, and then stick it onto the land and have it be okay. If you're going the other way, it's much easier. You can always kind of swim, and if you need to breathe, you put your head up. It's incredibly difficult, and it's amazing, that it happened at all. Things like insects and arthropods, it's a little bit different because they have a very different respiratory system. And there it really is air passing over the sort of book lungs, as they're called, that they have. It's much easier. It's not a coincidence that they got to the land first before the vertebrates. But I think you need vertebrates for intelligence, octopuses notwithstanding.
Why is that? Why? I mean,
Well, I'm a fan of vertebrate intelligence because you need to have one end. You need to have a nervous system in a tube so that one end can swell up and become a brain.
Oh, I see.
It's hard to do that otherwise. So I'm not sure, that may be wrong.
I see obstacles to contemplative life inside the sea.
Yeah. In terms of what the, it's just very hard to say otherwise what the conditions would be if you had multiple moons, and whether usually when you have the kind of moons that we're talking about, to have multiple moons stick around for 5 billion years is very difficult to do. You can get them to stick around for longer periods if they're tiny and don't really interact with one another. But the Earth and the Moon is almost a double planet system, so it really is very unusual conditions.
You mostly answered my original question about why going from land to sea is more common than vice versa. So I'll ask, are there any examples of a creature going from land to sea and then going back to land because it's already gotten a land-based respiratory system?
Not yet. Not that I can think of. It's a lot harder to do that now because something like a dolphin, certainly a whale, which has evolved to that it couldn't possibly be self-sustaining on land. But land is a lot more dangerous than it used to be. And kind of flailing around, waiting for something to happen, isn't going to cut it. So I think that's probably the end.
Let this be Steve's career advice to you.
Is there any mathematical models that sort of roughly describe the timescales with which the evolutionary processes take place? For example, the example of the tide pools, you do the chances of survival of fish with fingers and the chance of survival without fingers, and the lifespan of fish.
Yeah, it is the kind of thing that people do try to model, and this is very far outside my comfort zone. So what I'm dealing with right now is simply the empirical facts, that we have a reasonably complete fossil record of going from things that are definitely fishy to things that are, that didn't come out quite right, things that are fish-like, and to things that we identify clearly as some kind of a creature which has some degree of land navigation. And there's sort of a 30 to 40 million year period over which that transition is clear. But it's also what one learns when you sort of read this field is that it's constantly being surprised, simply because it's unusual for anything for a given creature to be fossilized. So the fossil record is incomplete. And we're surprised. We think we have kind of a reasonably coherent story that appears, and then you find these trackways, these billion trackways, and all of a sudden it turns out that not only are there tetrapods 20 million years before you thought, but they're already highly evolved, and you have no idea what the stem line was, which was obviously many millions of years before then. So I don't know what the mathematical models say, but for sort of what I'm kind of questions I'm trying to answer, the fossil record sort of speaks for itself.
Yeah, I just thought it could be interesting, like if you had a pretty precise mathematical model, then it could maybe.
So I'm not sure where the greater uncertainties would lie in something like that.
But I just meant then you would maybe be able to find some general constant for life on Earth that determines like how fast mutations in DNA take place or the frequency.
It sounds like kind of a holy grail of evolutionary biology. I think that's a hard problem, I guess, but one can aspire to.
Well, we have the rest of the evening to
sort that out.
deal with that. Right, please.
How could this be the great filter in Fermi's paradox? In other words, how common are rocky planets with big moons?
Yeah, no, good question. So I'm a SETI skeptic, and I'm a deep SETI skeptic. I'm a little bit more agnostic about life itself. I think it's much easier to have molecules that pop up that can replicate themselves, and then that doesn't strike me as being so completely bizarre. The history of life on Earth, the more I learn about it, the more I'm struck by how bizarre it is, and how there are so many things that people don't think are important, but actually turn out to be incredibly important. And one of them is the existence of the moon. Not only for the tides that it causes, but also probably for stabilizing the obliquity of the Earth's rotational axis. We see lots of planets that have crazy orientations, and over 4 to 5 billion years, that's what's going to happen unless you have some kind of a system which has been finely tuned so that it's stable and long-lasting. So yes, I think this kind of work, if anything, makes it less likely that we're in a universe which is just brimming with civilizations. Very much so.
It's the agreement, I mean the similarity of the observed sizes between the moon and the sun, and how good that is that still a little too good to be explained by this idea in the anthropic principle? Because I mean, I take the point that you have this fudge factor to the third, but factor of unity, or number of order unity to the third is nearly 1, but it's not exactly 1. And it seems like those two angular sizes are very close to 1. They're not sort of like 1.5 or 1.25 or something like this. So is there still a bit of coincidence here?
Yeah, I think there's still a bit of coincidence because, but it also, it's not something that will remain that good as a function of time, because the moon is in fact moving out. But we shouldn't be surprised, I think, that they're rather close. So something where you have an agreement which is within 5% or 10% is very easy to achieve. So having it, you're right, absolutely precisely the case is a bit coincidental, but it's nowhere near as coincidental as it would be if you just sort of slap them down at random. You can't have a lot of variations and have this sort of regular tidal pattern. You really have to be very close.
You described how one would need a vertebrate to develop the brain.
Yeah.
I think
I think it's easier for vertebrates to develop.
Okay, so my question is there a reason why it would be perhaps easier for land vertebrates than bony fish, because fish are vertebrates as far as I know? to develop sentience, or is that also a coincidence?
No, I think just being on land, and it's, I'm getting into a speculative realm here, that the combination of being a vertebrate and not having to use limbs or fins for constant locomotion all of the time. Certainly by the time you get to creatures that took advantage of trees, the feedback between eye, brain, and hand was probably a key part of the development of the sort of intelligence that we associate with humans. And I don't know that it can't happen in the sea. I don't see how.
So you're saying that because fish had to sort of spend more brain power constantly keeping themselves oriented and moving in the three-dimensional space?
Well, they didn't have the same sort of feedback processes, I think. But honestly, this sort of thing is, people argue about that all the time. And obviously, octopuses seem to have been done fairly well for reasons that are a little bit hard for me to reconstruct. So I'm going to have to leave that one.
Okay.
Well, just think about how difficult it is to preserve intellectual life on the beach. Maybe another question?
Oh, question down.
So the intellectual life has petered out. Right. Well, intellectual life hasn't petered out because we have a whole dinner in front of us, and it isn't for the sake of food that we're having it. It's
welcome.
It's so that we can continue this intellectual discussion at dinner. And in the meanwhile, let's thank Steve again.